We're now ready to look at the derivatives of inverse trig functions, but actually before we look at the derivatives, let's review just a little bit about inverse trig functions. Recall that if we have the inverse sine of x, essentially it's saying I computed the sine of some angle and I got this value, x. What was the angle? And in order to have a function, recall that we restricted the range or the angles to be values from the right half of the unit circle, so on the interval from negative pi halves to pi halves, because recall on the unit circle, sine is the y value, and if we take things from negative pi halves to pi halves, we will have covered all positive and all negative y values, but we will not repeat. Inverse cosine, we restricted it to the upper half of the circle, and then inverse tangent, we restricted it again to the right half, the interval from negative pi halves to pi halves for the range, and then we wouldn't have any repeats and we would have a function. Now on the inverse reciprocal functions, we just need to restrict this so that we cover all positives and all negatives and we don't repeat, but the trig book used by the college did the restrictions like is listed on the screen here. However, for our calculus, we're going to restrict them a little bit differently. For inverse cosecant, we are going to restrict the range, the angles, from 0 to pi halves, and that would cover the positives, and then from pi to 3 pi halves, and that would cover the negatives. On inverse secant, we're going to do the same restriction. The range will be restricted from 0 to pi halves, that would cover the positives, and from pi to 3 pi halves, that would cover the negatives. For inverse cotangent, our restriction is going to be the same as we saw in trig, from 0 to pi. So let's now look at our inverse sine. We've got a graph of the inverse sine function here. Our domain is then going to be what we would get for sine values if we had taken the sine of all these various angles, and that would be from negative 1 to 1. And our range then is that restriction from negative pi halves to pi halves. Now if we think of finding the derivative, first of all we can see that it would not exist because the function doesn't exist for values of x smaller than negative 1 or values of x greater than 1. But we could also see that there is a vertical tangent at negative 1 and a vertical tangent at 1, so the derivative would not exist there either. Looking between negative 1 and 1, we see that the slope of the tangent to the curve is always going to be positive. So those are a few traits we can see that must be true about the derivative. Now let's go ahead and compute the derivative. First we'll start with the function, and we are going to take the sine of both sides, and we know that the sine and its inverse will undo each other, so we're left with sine y equals x. Now we're going to use implicit differentiation. The derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. And our derivative of x is 1, so we could now solve this for dy dx. And we would have 1 over cosine y. Now that's great, but we'd like to express this in terms of x, and our connection with x is x equals sine y. So let's remember the fundamental identity from trig, sine squared y plus cosine squared y equal 1, and we could solve this for cosine y. In doing that, we'd have plus or minus the square root of 1 minus sine squared y. However, if we're looking at angles between negative pi halves and pi halves, we know that the cosine value is always positive, so we just want the positive of this. So we could take this and substitute it in for our cosine y. So we now have dy dx equal 1 over square root of 1 minus sine squared y, but we've got a connection between sine y and x. Sine y equals x, so we finally can replace that sine y with an x, so that will make this 1 over the square root of 1 minus x squared. We now have the derivative of the inverse sine. It will be 1 over the square root of 1 minus x squared, and we can see that some of these traits we saw that needed to be true about the derivative in fact are true. The domain of this derivative function would be the interval from -1 to 1 non-inclusive, because if we tried using -1 or 1 here, we would be dividing by 0. And if we pick values smaller than -1 or larger than 1, we'd see we would have the square root of a negative. So we are restricted to that open interval from -1 to 1. And we see that this will always give us a positive value. And we saw that that slope should always be positive. So let's go ahead and look at inverse tangent. We first of all look at the graph here and recall that the tangent function, if you compute the tangent for any angle, we could get values anywhere from -infinity to infinity. And so that's going to be the domain of our inverse tangent function. We restrict our range from -pi-halves to pi-halves. And this is non-inclusive because we know if we were computing the tangent that there are vertical asymptotes at -pi-halves and pi-halves. Hence, in the inverse function, they become horizontal asymptotes. So looking at our graph here and thinking what the derivative would do, we can see as we move out towards this horizontal asymptote, this derivative is becoming close to 0. As we move along the graph, we have a positive slope becoming larger. Looks like it's a slope of 1 right here, and then heading back towards 0, but always positive. Let's go ahead and compute the derivative. We are going to do this very much like we did the inverse sine. So first we will take the tangent of both sides, and then we will use implicit differentiation. The derivative of tangent of something is secant squared of the something times the derivative of the something. Okay, the derivative of x is 1, so we can solve this for dy dx, and we would get 1 over secant squared y. Thinking of our Pythagorean identities again, because we know how to express x in terms of tangent, we know that secant squared equals, now let's say you kind of don't remember this from trig, but you do remember the fundamental identity, because that one's probably etched in your mind forever. Now, we knew that tangent squared and secant squared have a connection, but if we can't quite remember the connection, we could start with the fundamental identity, and if I divided sine squared by cosine squared of y here, this would give me a tangent squared, and that's what I want to involve. So I'm going to divide everything by cosine squared, just reminding you how you could come up with this identity again if you didn't have it in your head. Okay, so this first quotient is just tangent squared y plus, this is just a 1, and 1 over cosine is secant, so this would be secant squared y. So here is our connection. Secant squared y is, I'm going to write it as 1 plus tangent squared y. So I can express this as 1 over 1 plus tangent squared y, but our connection is tangent y equals x. So our derivative is 1 over 1 plus x squared. So derivative of tangent is 1 over 1 plus x squared. We can see that this is defined for all values of x, but it will always give us a positive number. And that's exactly what we saw needed to be true about the slope of the tangent to this curve at any given point. Let's go ahead and look at the graphs. Here is our inverse tangent graph, and we can see the graph of the derivative doing exactly what we predicted it would do. Very close to 0 here. It's positive but becoming larger up to 1, and then decreasing but still positive and approaching 0. Derivatives of our other inverse trig functions are listed here, and they could be derived in the same way. The two that are commonly used and commonly occur, you're going to need those, and particularly in Calc 2 as we're doing integrals, we see these quite a bit, are the two that we derive. So these are the two that you need to have memorized. And if you look, the co-functions, meaning that have the co on them, look the same as their co-function except they have negatives. So inverse sine, we derived that and got 1 over the square root of 1 minus x squared. Well, inverse cosine's derivative is just the negative of that, much like the derivative of cosine was negative sine, so that will help us remember the cos basically have negatives on their derivatives. Okay, looking at inverse tangent, which we derived, if you looked at the derivative of inverse cotangent, it is the same derivative. derivative but with a negative sign. And we could also derive the other two, and here they are, and you see that inverse secant is right here, and inverse cosecant is the same as inverse secant but with a negative sign. And as I mentioned, these inverse sine and inverse tangent are the two you'll want to have memorized. So let's go ahead and apply this, looking at an inverse sine. Now this is not an inverse sine of x, this is an inverse sine of some stuff. So basically we could call that u, and we know the inverse sine was 1 over the square root of 1 minus, in this case it will then be u squared, but then we've got the chain rule applying, so that we would then need to multiply it by the derivative of u. So let's go ahead and do that. As we identify this, our stuff, or our u, is 2x to the third. So in computing this derivative, it's going to be 1 over the square root of 1 minus, right here we need to put in 2x to the third and square it, and then we need to multiply that by the derivative of this stuff, and the derivative of this will be a power out in front, multiply to the 2, give me a 6, x to the decrease the power by 1. So our derivative is going to be 6x squared over the square root of 1 minus 4x to the 6th.